Okay, so all are there. Can we start?
Yeah, can we start.
So yesterday I gave already an introductory lecture to semantic web. Who was not there? Just give me a sign. I just want to know who was not there. That are 1, 2, 3, 4, 5, 6, 7. About 7 people. Just that you know what I have done there. I gave a short introduction to myself, then also a short introduction to semantic web, why it occurs, what is the topic, the main topic about make a machine processable web. And then I also showed, which is also more important, two things, okay, industry already applies semantic web, and the other, which is much more important, is what are the limits of semantic web, where you should apply semantic web and maybe where not. So, where you should apply traditional software, because the computation, algorithms, and so on are too easy, such that semantic web has too much complexity, too much overhead right there. And the other things is that the point that some things are more meaningful to be done still by humans. You know? And between is the semantic web. So the semantic web wants to move the border of the things, what can be done by the computer and not by humans. So that's the main thing. I heard, I don't know exactly if you already got it, some electronic copies of the lecture slides. Did Professor Chandrasekharan already distributed in some form to you? Not yet, but you will get. And for those who have there especially some questions to the topics of yesterday and were not there, please ask me about this. If there are any questions. And also if there are any questions, please ask. You can also interrupt me during the lecture. If it not becomes too much questions, then I will answer this right at the slide where I'm just talking. Just give a sign, a hand, something like that. And then, I give you the opportunity to ask a question and we will just go on later. Okay, are there any questions about this yet?
How is linked data different from semantic?
Okay, linked data we come later to this. So that is one thing. Linked data I will, the 5th or 6th lecture I will talk about this. I would now just say, okay, if you have on the specific topic which is there, have a question, then just ask. If it is completely different, then just wait a little bit to the coffee break or after the lecture, because then we don't come to the end. But there will be enough room to give you answers to this question. Is it okay for you? Okay. Yesterday we did introduction and the vision of the semantic web in short. Today we go already into the details. I want to give a very practical lecture. That's the point, and we will therefore have to deal with the specific specifications so that you can apply semantic web technologies. I already showed you yesterday also, this core of semantic web specifications right there. There are a lot of other outside, but all of them which are outside rely on this core of specifications. In this lecture we will come to all of these specifications right here. We will learn all these specifications, more or less complete. Some holes will be there, of course. But yeah, I think we will get to the point that you have enough knowledge to really apply the semantic web technologies right there. The other things which are outside the core of these semantic web specifications, we will not deal with because I cannot present them all, and I also want to give you some insights into some research topics. And the research topics, because it's my favorite and my main topic of research, will be about data management in semantic web. So something like how to do query processing and query optimization such that you can achieve query results very fast. Something like that is my main topic, and we will talk also about this. Today we start with RDF, also very short. You will also learn the syntax of it to really apply them in practice. And then I would say today is the official SPARQL day, because today we do SPARQL the whole day, also with the practice in session afterwards. So for the tutorials, you need your computers. I hope you have computers at hand. In the late afternoon, we will have a practice in session where you can try out your first SPARQL queries and so on. I have prepared some web page where you can do online some queries right there and test them out. Okay. That's the topic of today. So we start with the data model because all other things are relying on top of it. RDF is officially called the Resource Description Framework. It's the long name of RDF. Some also say, instead of framework, sometimes or often you hear also format, resource description format, because some say, okay, it's more formats than a framework. That is just the name. But the data format, is the one officially designed and recommended by the World Wide Web Consortium already in 1999 to describe resources, as the name states, but it can be also used for all other data. You will see it, and it is already used also for all other data. The form of the data, its components, are quite simple. It's only a set of tuples right here. So that is different to relational databases or something like that. In the relational model, you have tables, and the tables can have a lot of columns, an arbitrary number of columns. Here we have tuples, and all tuples consist of 3 components itself. It's much more simple, and we will later see that we can utilize this simple definition of the core components of its data to optimize some things like query processing. So if you have here an arbitrary number, then surely you can't optimize something or optimize less than you have here a fixed number of components. But on the other hand, maybe you sometimes have some overhead to really express the data itself. That's also the point, because you have tuples with latency. Okay, lists and so on must be also represented by triples, by a set of triples. Okay, that's it. We have always three components. The first is called the subject, the second the predicate, and the third the object. Just related to a very simple natural sentence. Then you also have the subject, predicate, object right there, and it's also it's also the way to describe maybe resources. For example, the computer has the color blue, something like that. You can visualize the triples as a graph. So we call an RDF dataset very often also an RDF graph. And you do it by introducing unique nodes for the subject and object. And the predicate is a directed edge between the subject node and the object node. So you will get then from your set of triples a directed labeled graph. Labeled because the edge is labeled with the predicate, and directed because it's a directed edge from the subject to the object. So here's an example, just article 1 is of type article. If there comes more triples right there, and we have some common nodes, then these common nodes remain as unique nodes. So the second triple here is article 1, creator, person 1, and has the same subject node article 1 with the first triple. So here we have, it's just a small running example which we will later also use. Here we have another triple, person 1, name Martin. And here it is the case that from this last triple, the subject node is the same as the object of the second triple. So also subject and object nodes can fall together as unique nodes. Okay, that's it. And you can now think about, and you can already learned that you can have a lot of triples, and all these triples then represent a graph. As I said, today we already make a lot of details so that you can really practice it in the tutorials. The different components of the RDF data are basically the internationalized resource identifier, plain nodes, and literal, and I will give you a short introduction to all of them. I think I will just switch on because I will talk about this later on in more detail. I will just go on with the slides, and I will show you that the domain of triples is not so straightforward that you can use all of these types right here at every position in the triple. You can, it's more like this, that at the subject position you can use iris and blank nodes as property. The second component of RDF triples you can only use iris, and in the object position you can use all these different types of RDF terms, iris, blank nodes, and literals right here. That has some historical reasons, because when you think about that you have somewhere a subject, predicate, and then object, for example, you can think about that the object, or it is only meaningful that the object can contain the values which are expressed here as literals. And but it is not so original. So sometimes this is also not so very vital. So I'm just becoming warm, so I will take off this, although it's a big honor for me to get this. We will go on.
Excuse me.
Yeah.
I have a doubt in the previous slide.
Yeah, but
how are you saying I like union B? Why do you say that triple belongs to I union B? How are you saying that?
A triple, it's the domain of a triple. So a triple is contained in. So that this is somehow the signature is contained in the set of all possible values of RDF data of triples, and the set of all possible triples is really the set of Iris, union, the set of blank nodes, the cross product with Iris, the cross product with the union of all types right here. Does it explain it?
No, I'm not able to understand like why separately you have shown I union B, and why are you applying the cross product there?
A cross product here.
Why are you applying that?
I'm doing it right here because it is really on the right. It is really the set of all possible values for triples.
Okay.
It's okay. So this means okay.
Okay.
Yeah. Okay.
Can it subject take blank node as blank means it will
Blank nodes, I will come to the next, on this next slides. Blank nodes are some objects without a name, just some intermediate nodes. You know, because sometimes you don't want to have a name for all the different, all the different nodes right here. You don't want to introduce specific names for it, because otherwise at some point you don't have any names anymore, or that is maybe not the main reason, but you will use the same nodes for different things at some point. For example, you will say, okay, this is element 1 of a list, and the later you will also say element 1 of the list. And then you will have a problem, because you have different, the same identifier for different things. And so we will introduce, or the semantic web community introduce blank nodes. I will show it later on also. Okay, are there other questions? The RDF data itself can be serialized in different forms. Originally, it was introduced the XML-oriented approach, where you have RDF XML. It's also a recommendation. But we have also a lot of triple-oriented serialization forms. And three, turtle, and triples, and so on. They look basically all the same, but have on top of it sometimes some different language constructs. We will consider here only the triple-oriented, not the XML-oriented. And also there are only the core right here, which are all in common for all these different serialization languages. Okay. And one question, or one reason why we don't look at the XML-oriented, the triple-oriented is much more easier for humans to read, because you really see the triples. And RDF XML, the XML-oriented, you sometimes don't see all the triples which are really inside there. So it's sometimes really difficult to see all the triples which you express with RDF XML. Sometimes there are more triples inside than you will know, and another reason is you can very easily, with online converters or other tools, transform RDF XML to triple-oriented serialization formats. So if you at some point need RDF XML, or you have RDF XML as source data format, then you can transform them, and then you see the triples and can work with it. So that are some few arguments to first start with this, because anyway it's more easy for beginners, right? Start here, and you don't really lose something. So now I will go to the specific components what's there. First, internationalized resource identifier. It is an extension of the uniform resource identifier URI, and just extended by having allowed some more characters which are not allowed in URIs, like some special characters of some other foreign languages, Korean or Chinese letters and so on. They are allowed in internationalized resource identifiers and not in URI. In general, it is like this, that you that the form of iris are very much looking the same as URLs. They are not really URLs, so behind these these addresses, they are not addresses, but I just think in the way of URLs. Behind these possible web addresses, there doesn't need to be some content behind. They are just identifiers. It's called identifier, and they are just identifiers. But sometimes it is good practice that behind this term, if you have access to that domain, web domain right there, to put there behind it some component, some web page which explains the addressed entity right here, which you want to express right here. It's good practice. So, why we want to use, or why is it good to have a so long representation of something? You know, you could also just call it index and not http www example.org index. It's a very long representation, and of course that means also very big overhead. It's much verbose, and it means very much overhead right there. Why you should use it in this way? So there are some reasons. One good reason is that with a so long representation, the hope is that this identifier becomes also unique right there. If you use, for example, here as prefix, not www.example.org, So most probably also other persons will name it for other purposes. But you use maybe your own domain name here, which is under your control. Then most probably no other people will use your domain, your prefix to have names for their own queries. They most probably will use their own domain right here as prefix. And of course, this not fully guarantees that other persons maybe misuses your queries right there, but at some point it helps to prevent these cases. Good. And of course, some queries maybe should be also used by other person if they refer to the same thing. Then maybe it's also good that they use your prefixes, your queries, not prefixes, your queries with the defined meaning behind it. Okay, they look like URLs. Here's also the syntax expression right here, which also is the same like URLs, where you have here the host and then a path behind it, then the fragment. Here's an example for a fragment right here, and so on. It's really the same as URLs. I don't want to go into details right here. I think that you can read. Of course, you don't want to write always these long queries. So you want to have some way to shorten it, and the normal way is to use prefixes, aliases, namespaces that are all names for it. And you can make a prefix declaration in this tuple-oriented languages just by, in the beginning of the document, just start with @ then with the keyword prefix, then the prefix name, a column, and then that part of the query which you want to shorten, such that you can later on just use the syntax prefix colon postfix for the queries. In this example, we have declared a prefix for XML schema data types, which are also all supported by the semantic web languages. There you can use all of the 37, something like this, something around 37 XML schema types for all the different integer representations, string representation, date, time, and so on. So that is also quite, or the W3C also took much care that things they already have defined are reused in some other languages. And this is one example. So they reused, for example, the XML schema representation or the XML schema language for the data types in RDF and in SPARQL, in RIF, and so on. And they also reuse, for example, SPARQL in some other recommendations of them. Okay, we are just here at the example. We have here the example XSD integer. XSD is a prefix, integer is a postfix, and it is just like this, that this is equivalent to the long form, where here the prefix is just replaced by its alias, So here from HTTP starting with XML schema, and then the postfix is just appended behind. And that are different representations. You can also use, it's also allowed that you have here different prefixes for the same alias, but it's not meaningful. But anyway, it's also just a minor remark. So then we come to the blank notes. That is for something without a name, in short. You could say like this. And I already give some example. Blank notes are always used if you want a local identifier which you want to use in one document, but you don't want to give a global identifier, global name for it, because this node is not really important at that point, just a clue for other information, just an intermediate node. And you don't want to, or it's not necessary to access this node directly later on. The syntax is just these square brackets. Then you don't really have, or you don't see any name there. Any occurrence of this square brackets is another blank node, not the same blank node. But within one document you can also give a local identifier. Then you just start with this underscore, then a column, and then the name of the local identifier. And the point is that here this local identifier name is only valid during the current import of the RDF data. Such that in the same document you can really address this blank node another time, as often as you want, but only within this local document. So the local identifier name is not persistent. And name cannot be reused after the import to access this blank node, and you can only indirectly address it by addressing other nodes around it. Good. And the last points, I also said it sometime, but here it stands more explicitly. Blank nodes with the same local identifier, for example, underscore name, in different sources are different blank nodes, but they are important to know. Now we come to the last type right here. Last type of RDF terms. It's literal, and that are really the values of semantic web data. There are also three forms of it. The simple one is just a string. Enclosed in apostrophes. You can also additionally give a data type. So that is a data typed literal. You just start like the ones of the simple literals, just like them, and then you do some circumflexes, and after that you give the IRI of the data type. And that could be, again, for example, XML schema data types, but it could be also own data types. There's an example. For example, here www.xorg my app data type is not defined officially anywhere. So you can introduce your own data types and use them right here. But the interpretation of these own data types you must still implement in the somewhere in your application, you could say. Okay. Then you already, yeah?
The last slide, can you give an example for a blank node? Last slide.
Last slide.
Yeah.
Yeah. An example for a blank node?
Yeah. Then is it not necessary to give it a name?
For example, if you use lists, and for the lists you cannot express or you cannot express a list of elements in one tuple, so you must use intermediate nodes to say, okay, this represents the first list element, and the value of this first list element is this, and then you have a pointer, you could say like this, a pointer to the rest of the list. And all these intermediate nodes for representing the current list elements, you don't know, or you don't need to know their names, you just must have a blank node between them to glue all these list elements together. Is that this? Okay.
Can you just write that example on the board, please?
What?
Will you be able to write that on the board?
Of what?
Of what you explained?
It will come on some of the next slides.
Okay.
You are always a little bit before my slides. I have to reorder my slides because you are already thinking about the next steps, and I don't have them at the right place right here. Okay, just I wanted to mark out, of course, the series of data types can be presented in prefix, postfix notation, or in the long form, and so on. And strings with the data type XSD string are equivalent to the simple literals. They are not the same, but literal from the RDF semantics. And the third form are language tag literals. There you have first some simple literal, and then you have add, and then you have a language code. For example, hello at GIAN means, okay, that is an English word or an English sentence. So you have multiple language support just right in the data model, which is also very fine, because for other things you always must put them into the application when you have already it integrated in the data format right there. So, and hello in English means hello in German. So that is the first word maybe you learned in German. So, welcome to an introductory course on German, but afterwards you must also explain me your language and give me an introduction to it. But I'm afraid maybe I will be a very complicated student. I'm already old and don't learn so fast anymore. But anyway, we must concentrate on the topic. Here's our first full example of RDF data. Here we have a lot of prefixes, first declared, and you really see in this triple-oriented serialization format that you really see the triples right here. The first triple starts right here. Bench publication is the subject of the tuple. RDF S subclass of is the predicate of the tuple, and bench media is the object of the tuple. That is the first tuple. Here we have the second one. Here we have a third one, and here we have a fourth one right here. So fourth tuples are in this RDF document. Okay, and it describes here that we have a journal. This name, it's not original, why it's not so intelligent name, but it's from some benchmark data, 1940, with some title. And here we have already a small ontology. Journal is a subclass of publication, and publication is a subclass of media, right here. That's it. I also, because it occurs very often, want to give you a syntax sugar, but if you already understand the serialization format, then already you have learned quite a lot and can express all the things in RDF. Now, here I only have some small syntax sugar around it. So computer science are normally sometimes a little bit lazy. It's, I would just say at least not they are hardworking, but when they want to write something, they're a little bit lazy. I just state this. Maybe you agree or disagree, but they don't want to repeat things, at least in this. They hate redundant things. And some redundant information doesn't need to be repeated in RDF data. For example, if you have a lot of triples with common subjects and predicates, then you don't need to repeat them. You just write the subject and the predicate one time. Then the first object of the first tuple, the second object of the second tuple just behind and separated with a comma. And in this example, the third object of the third tuple also becoming here the third, just write the third object here and separate it by commas, and then maybe I didn't say it explicitly, all the tuples are separated by dots. Okay, that's it. So this long expression becomes much shorter. Another way to shorten some things is that we might maybe sometimes only have the same subjects and not the same and different predicate and objects right here. And you can really, in the tuple-oriented languages, you can really have another short name for it. Just write one time the subject, then the first predicate and object of the first tuple, then it's called in English also semicolon? Semicolon, yeah. It's also called semicolon, then a semicolon, and then predicate object, and then just quit, finish with a dot right there. Okay, that's it, but they don't come to the idea to have some subject lists or something like that. Maybe sometimes also necessary, but they didn't have this idea, or they didn't want to implement it. And of course, you can you can mixture object and predicate object lists right here. Just very short, just you have seen it, and then we go on. blank notes can be expressed, as I said, instead of a local name, also just by this square brackets. Yeah, square brackets. And then, for example, you see a predicate and object, but you can also, that you must also know, represents exactly this expression by putting the predicate and object inside the square brackets. Just like this. And it has one advantage. You can write something before and behind. And if you write something before, then you can use a subject and predicate before, and you have an additional tuple with the subject and object, and the blank note as object right here. So this is equivalent to bookshop 1 sells some blank notes. I just introduce here local identifier for the blank note, and this B must not be used elsewhere in the document, of course, otherwise it's not the same. Then the same blank note as subject for the expression which stands here a bit inside. That is the second line, and if you write something behind the square brackets, then the blank note becomes the subject of what stands behind it. So, okay, here we have a semicolon, so this B is repeated right here. So this blank note B is also the subject of rise 10 of type XSD. Yeah.
What if there are multiple blank notes in a file?
In
a file, there are multiple data source. There are multiple blank notes, and you are using convention of using square brackets. So how do you differentiate between two different blank notes?
So I don't know if I fully understand the question, but the thing is, if you use the square brackets, then it's every time a new blank note, even within the same document. That is one point. So if you use another time this square bracket, even within the same document, it's another blank note. And if there are many documents, of course, that are also then different blank notes. And of course, this is also sometimes good because then you don't have the burden to also within the same document find every time different names for the blank note. Does it?
Yeah.
Okay. That was the question. So explicitly stating explicitly the remark that square brackets, every square bracket is another blank note. And not the same blank note. Okay, then we come to the RDF collections. That is the example I already referred to before. You can also represent lists in this people-oriented serialization formats just by using normal brackets and writing the list elements inside. And I think that is the last syntax sugar which I will give right here. And this is equivalent. So here we have a list with the elements Friday, Saturday, Sunday. And this is equivalent to the following expression, that we have a blank note right here for the first list element, this blank node then refers to the value of the first list element with RDF first Friday. Don't ask me why they call it first. I don't know actually. So with RDF first Friday, and then they refer to the next or the rest of the list here with RDF next. So here we have again a semicolon. So the same blank node, RDF next, with, yeah, again, the same representation of the rest list right here. Then it goes recursive, one after the other. Here we have also some representation of an RDF data editor where you exactly see the RDF graph. There you have also here some blank node. Here we have again local identifier, B0, RDF first Friday, B0, RDF next to the rest of the list, and then it goes on. B1, RDF first Saturday, B1, RDF next to the rest of the list, B2, RDF first Sunday, and B2, RDF next, RDF near, and RDF near represents the end of the list. And that's it. Okay, is that clear? Very nice, very good. And of course, if you have here brackets, then you can write something before and behind, and you can just replace here the list representation with the one where you exactly see the blank nodes, and then you know how to resolve this. Okay, I think that it's, except here you really see that computer science are a little bit lazy. So blank node RDF type bench journal there can be a much shorter representation be a bench journal. So it sounds something like a baby language, but that is, I think, the really the most short name, the shortest name, so the shortest name of something. Just one character, be a journal, right here. And of course, if you only write brackets, simple brackets, then it's equivalent to RDF. Okay. Yeah.
Do we need to write some prefix for the short names, or it is for the default? Should we write some prefix for the short name, or
some prefix for the short names? No, these short names like is just
is for RDF type?
Is for RDF type. So RDF, of course, is some commonly used prefix for some eerie
RDF subclass of RDF subtype of.
I didn't understand.
Like RDF subclass of.
Genau, like RDFS subclass of, where RDFS is some prefix which is commonly used for longer eerie, for the RDF schema vocabulary, and RDF is also one for the RDF vocabulary, and OL is for the old vocabulary. And yeah, what's
is this? Should we write some prefix for short names, or RDF type is the short name is only for RDF type, like A replaces
for RDF, you must also have a prefix declaration before. So it's not complete. Is that the question?
No. For the short name, do we need a prefix?
For this
short name, like RDF type represents is an alternative for A.
So for this A, we don't need a prefix. It's just A. just A and that's it. Of course, if you here use RDF or all or something, I know it was not your question, but just a remark, we must always also have before the prefix declarations for RDF, all RDF schema, although they are commonly used. Just otherwise, the semantic web tools don't know them. It's simple like this. I think your question was now answered. Other questions so far? So now I think you can already have the syntax of RDF. It's just the basics that you can express your data with RDF. We are already at this point. As I said, very practical, we also must look at the syntax so that we can really do exercises with semantic web tools. The next point is that we want to look at a query language like SPARQL. And I will introduce also SPARQL 1.0, most of the things, and SPARQL 1.1, also most of the things that you can really handle, because SPARQL is one of the query languages, or is the query language most widely used in semantic web tools, so it's very important to know its basics. If you know already SQL, I presume you know already SQL, then it's relatively easy to learn SPARQL. So some things are different. I will also show you where SPARQL goes behind SQL. Of course, sometimes SQL, at least in the modern specifications, they are also going behind SPARQL, but for some things, SPARQL is also much more powerful than SQL. I will also show this at least from standard SPARQL compared to standard SQL. So SPARQL first stands for SPARQL Protocol and RDF Query Language. So SPARQL stands for SPARQL itself. So it's a recursive acronym. I have to look. There is especially also a name for it right here. I think first it was they thought about simple protocol and RDF query language, but maybe simple is not a good name for a standard, so they exchanged it to SPARQL. What to do with it is exchange it to SPARQL. You can call it a graph query language for RDF data. We always have to discuss where it is really a graph language and so on. But you can call it a graph query language because you also address and query RDF graph. So it's a graph query language, that is one thing. And the same way you can express graphs in RDF, in the same way you can express queries in SPARQL, you could say like this. It's a recommendation since January 2008, and SPARQL 1.1 was defined, I'm not sure, but 2011 or something, I must look. All is recorded, I don't have to make mistakes. I have it on the next slides. So, SPARQL 1.0, there are some papers, is as powerful as relational algebra. Who already know about relational algebra? You just give me a sign. There are some, but many also don't know relational algebra. So I will also explain something to relational algebra right here, because I want to put it into relation to SPARQL 1.0. SPARQL 1.0 is quite easy. They really developed it first because the semantic web tools developer should go and really implement SPARQL 1.0. It should be very easy to them to support SPARQL 1.0. So they first didn't put so many features inside. It was really a strategic decision. You know, it's some form of strategy to say, okay, give very first a rudimentary language, such that because there are already before were many different semantic web query language which were all proprietary and which I think now all disappeared, RDF and so on. And they really also followed W3C and really all then implemented then SPARQL 1.0. So that was really a successful strategy. First, really provide a rudimentary query language, and then later on there was a big jump to 1.1, SPARQL 1.1. So when all implemented already SPARQL 1.0, yeah. Anyway, they were already on this train with SPARQL, and so they could really extend the SPARQL 1.0 specification with much more features, more than this 0.1 shift here in the version number suggests. And yeah, and with SPARQL 1.1, SPARQL becomes very powerful. We will see. And what was also very important is that additional protocols were defined for accessing remote SPARQL query servers, which are called SPARQL endpoints. So the SPARQL endpoints can run on any machine in the internet, and the protocol to set up queries to them, and also the result format of the results are specified in some additional SPARQL recommendations. And that's also here in the name SPARQL protocol and RDF query language. And that is very important because that means we can access any SPARQL endpoint somewhere in the internet in the same way. This is very important also for it's not data integration, it's how we go. Yeah, SPARQL query server integration, we could say like this. And there are a lot of SPARQL endpoints already running in the internet. On later slides, I will also provide some examples for it. And it is also an ideal playground for research on these topics, on distributed query processing and so on. Can really deal with real-world query servers, endpoints which are somewhere in the internet and can access them and can set up queries, sub-queries to them and get the results and so on. Okay.
So,
yeah, one question?
yeah. How do you say SPARQL 1.0 is as powerful as relational algebra? In terms of efficiency?
Yeah, first, is what you mean is in terms of, I just said, okay, SPARQL 1.0 is a rudimentary query language, not in terms of efficiency, in terms of language features. That's the thing. For example, if you know SQL, then SPARQL 1.0 doesn't have an opportunity to group things, group by. Comes with SPARQL 1.1. Something like that. But of course, efficiency and so on must be looked at, and some things are inside SPARQL 1.1 so that at least you must question yourself about how efficiently can this be implemented. That was also a discussion for parse expressions in SPARQL 1.1, but maybe we will discuss this maybe in the afternoon, something like that. Okay, I already asked who knows relational algebra. Some of you know. And I will always put SPARQL into relation with relational algebra. That means that I will show, at least at some examples, the transformation of SPARQL expressions into expressions in terms of the relational algebra, and which expression is behind the SPARQL expression, which expression of the relational algebra is behind the SPARQL expression, because if you know relational algebra, then you already have then a feeling for the semantics of SPARQL at some point, if you know the transformation right here. And you have theoretical grounding of all the things. You could say like this. Okay, relational algebra is the basis of SQL and also of SPARQL. Some few points are different, especially if you come to the triple patterns, something like this. And I will also come to the point that we have some common criteria for good query languages. I will also give some slides on this, and one point there is that each query language should be at least as powerful as relational algebra. That is some good design strategy, so that you can express enough, that you can have enough expressiveness for some common queries and query types. It's also called the relational completeness. But you must also know that relational algebra is not Turing complete. And that means that you can do not as much as you can do in other programming languages like Java, also JavaScript or C++ or something like that. So you cannot express every algorithm in SPARQL or in relational algebra, something like that. There are also some limits, like recursion you can't do in SPARQL, and also in the original versions of SQL, and also there is no possibility to determine the transitive closure in the relational algebra at first. There are later some extensions where it is the case, but if you look at the traditional relational algebra, then you can't express it. So, you say, okay, that's not good, it's not Turing complete, that's not good. But the good point is, because we have these restrictions, it is much better optimizable. You can much better optimize queries than programming languages. And there can be much faster processed on big data and so on. Because of this feature. But that is one big, there are always advantages and not disadvantages. And this is really one reason why you should sometimes restrict something, because afterwards you can much faster process it. that's the deal right here. Okay, with that, no questions here? Then I just have here some general criteria for query languages. So if you are working in some standardization committee for some query languages, then you should yeah, just for a moment, then you should look at these criteria such that your query language fulfills these criteria. That is maybe a good deal. So your question is?
How do you say? You say there is relational completeness in the previous slide. You were speaking about relational completeness.
Yeah.
And you finally say that transitive closure is not possible. Then how do you say it is how do you say there is relational completeness?
That what is not possible?
Transitive closure, no possibility to determine the transitive closure.
Yeah.
Transitivity is also a relationship, right?
It's also a relationship.
Transitive, no? If there is no transitivity, how do you say it is a complete relation? I'm just asking this.
If I say that it's not transitive closure, yeah, transitive closure, you can't express transitive closure with relational algebra. With the minimal set of operators in relational algebra, you can't express transitive closure. That is one thing. And I think your question is somewhere related with this. So the thing is that there are some extensions of the relational algebra which we don't consider right now, right here, where you can also express this, but we are not dealing with it here. And so relational completeness needs also there are some restrictions. Okay, that answers the question. Very fine. This lecture unit. We are just now at the criteria for good query languages, which everyone, if you design a new query language, everyone should consider, and we can also, of course, discuss if SPARQL, if the SPARQL query language or any other query language conforms to this criteria. One good way is that you support ad hoc formulations, that you can very easily express a query and that you don't need to write a whole program for it. You just say what you need, and you don't express, sometimes they are related, you don't express how you come to the result right here. And then you are already there that you should support declarative formulations or descriptivism. So just excuse sometimes my pronunciation. So you don't want, or it's much easier that you just say what you want, that you make a picture of what you want and just write it down. I want this, and this as a result. And you don't want to write down a complicated algorithm or something. So first, retrieve these people, and then I search the triples for those having as predicate RDF type, and then I use this object, or I also search other triples with another predicate, and then I want to join the object with with the subject and I use this and that algorithm for it. I use the hash one algorithm or something like that. You know? You don't want to express, oh, I want to use this algorithm and the algorithm looks like this, and after that I check this and so on. You don't want to write down it in a complicated form. You just want to make a picture, this and that I want, and I don't want to describe how you can achieve it. You want that it will be very much optimizable, that you can optimize it very well. And for this, the query should be mappable to basic operations. Very simple basic operations. Then we come to the operations of the relational algebra. And if you have very basic operations, then it is much easier to find optimization rules for this basic operations. That you maybe find, okay, I have this basic operation and this, I can exchange the order. And if I exchange the order, very much of intermediate results are avoided or something like that. And then the query is much faster processed. So that is very good if complicated queries, any complicated query can be expressed in very basic operations, which are done after the other, which are executed after the other, and I have transformation rules or optimization rules for it. Good. Another good criteria is that it is somehow set-oriented, that you have some well-known operations already for this set of results, set of intermediate results. For example, intersection, union, and so on, difference, and so on. So these operations are, I think, very much known by you and by normal people. They very often operate already in daily life with sets, and so set orientation is quite a good thing to achieve for query language. Then another good thing is such that you can very easily express queries, that you have the closure of operations. That the result of some operation is again a relation, or in general somehow of the same data format, data type as the intermediate results at any point, and can be input of the next operation. And then we can have nestable expressions, and here I should also, here it comes, and with this you can very easily have orthogonality, so that language constructs are in similar situations usable in a similar way. So if you at some point have some computation, for example, to bind a variable with this value, then later on you have the same computation in some Boolean expression, then it should be expressed in the same way here and there. Then it is very good, because you only need to know this syntax and can it reuse this syntax and in different situations, and you don't need to learn as query or as user different syntaxes for the same query language. You should use their, or you should learn only one syntax and reuse this syntax everywhere in the query. It's also very good design criteria for query languages. And of course, adequacy, we want to support by supporting all constructs of the subjacent data model. That means if you have our triples, that's hard. This triple notation should be somewhere reusable in SPARQL, the SPARQL query language, and of course, if there are EMS blank nodes and literals inside, you should also have this components in the SPARQL query language. That is quite clear. And there we see, okay, with the blank nodes, it's another thing we cannot directly access. Blank nodes, I will come to this point later on. So there we will see that blank nodes in RDF data and blank nodes in SPARQL queries are different things. But that is another point. Good. Then of course, all the things should have a high performance if we want to execute the query. Especially each operation should be efficiently executed. That is one thing. And in the relational model, we have for each operation, we have a complexity of n squared. With n number of tuples in the input relation, okay, if we have two input relations, one with n is the number of tuples in the one input relation, and m is the number of tuples in the other input relation, then we have a one-time complexity of n multiplied with m. And that's all. Of course, for big data, this is also too much. But for not too much data, it's already well. And of course, for big data, at most n multiplied with logarithm of n should be the highest complexity. But already quite fine here, and for these operations have this high complexity, they should be executed at a point where are only few intermediate results. So we should optimize all the things such that operation is high complexity. The typical way come very late in the execution pipeline. Okay. Then each query language, there should be some safety. So syntactical correct queries should deliver finite results and terminate. So no infinite loop and no infinite result should be there. And that is also different to programming languages where it's very easy to express infinite loops. But here, for query languages, it's a good design strategy to have everywhere finiteness, so that you know the query execution will end at some point. And we should have some completeness. I already said it before, so the language should be as powerful as a standard language, like relational algebra, so that we know we can express enough queries right there in this language that the typical queries can be all expressed in our newly designed query language. Okay, that are right here the criteria, and of course they were all also considered when the SPARQL query language was designed. some things maybe we must discuss if they are completely fully fulfilled, but in most times they are final. They are minor things, and okay, and some other things like the safety. We must also think about that. We have also some ontology languages like all and all full. We come later to it. Is undecidable. So if you have a query on top of RDF data, and ontology inference should be considered, and there are constructs inside which makes it undecidable, the inference is undecidable, then the query language also can be decidable on top of it. But the problem is then not the query language, it's then more that all full is undecidable, excuse me, right here. Okay, so for the query language, we are all fine right here. That is just one point to be considered. Then we come to the basic form of SPARQL. I know some of you are already experts right at this point, but for most of you maybe this is also not known so far, so we have to come to all this basic stuff right here to come to the higher topics, you could say like this. So the basic form of SPARQL right here starts also with prefix declarations. They look similar to the basic to the prefix declarations of RDF data, but here no @ symbol is before, just prefix. Then the prefix name, colon, and the alias, the IRI of the alias, and no dot. You just have to consider this. Then we have here select queries right here. This dot 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 means there can be a lot of prefix declarations, of course. Then we have here a select query. There are different types of SPARQL queries. The select query is the most common one, where you just like in SQL behind the select keyword, write down all the columns or variables which should occur in the result, and if you use a wildcard, then you want to have all the variables which are inside the SPARQL query. Okay. Of course, you can also want to have a duplicate elimination of the results. Then you just must add the distinct keyword. Right here it's also similar to SQL, and if it doesn't matter if duplicates are eliminated or not, or how many duplicates are eliminated, you can also write here reduced is also another keyword. Then how many duplicates are eliminated is up to the SPARQL query engine, just to let them more freedom for query optimization purposes. Then we have here the where part, where we have a lot of triple patterns inside and other constructs, which I will come later to it. And the triple patterns first look very similar to the triples of RDF data. But now you can also declare or use some variables inside, instead of only IRIs, blank notes, or literals. And it's a pattern, so this triple pattern filters input tuples, and it requires the equality if here are some constants inside. So this means this tuple pattern filters those tuples, and only those tuples remain for this tuple pattern where the predicate is RDF type and the object is French article. All others are left out, and the subjects of these tuples are bound to the variable article. Okay, then we have another tuple pattern right here. It goes the same way. Here only the predicate is a constant, so all tuples are in the intermediate result, you could say, of this tuple pattern, where they have a DC creator as predicate, and the subject is bound to the article variable, and the objects of these tuples are bound to the variable person. That's the basic thing. Then we come to the point, okay, we have now two intermediate results. They are all applied on the default graph of which is inside all the input data in the SPARQL database. We have two intermediate results. Here we have intermediate results where are bound values to the variable article, and here we have intermediate results where the variable article and person are bound to values. And now the results of these two intermediate results are just joined here, right here. It's similar to a join in SQL, or it's the same, you could say it's the same. If you are more coming from the prolog or data log area, you could, it's the same as having here an n combination, or in prolog or data log it's specified with a comma right here, something like that. And the join, of course, I think I have it also on one of the next slides for those who are familiar with relational algebra. Combine those tuples of these two intermediate results which have in common variables like the article. Article is occurring 2 times here in this tuple pattern and in this tuple pattern, which have the same values that are combined as one result and will occur in the result of in this time of the will be right here, if there are no other things. And the rest is just throwing away if there is no match in the values. So I will have also another example right here, and this is more top level. We can also make it more graphically. So here we have our two tuple patterns and also a third one. We can, in the same way as we build the RDF graph, we can here build a query graph just by combining here the 3 different tuple patterns, and each tuple patterns are expressed in this graphical representation. The subjects become subject nodes, and objects become object nodes, and predicates become a labeled edge between these nodes, and the nodes are just unique. It's the same as for RDF graphs. So, and then we have our RDF data. This is our running example from before, just in the beginning of the lecture. we have here our RDF data, and now you could match this query graph with the RDF graph and then get the result of the overall query. So, and it is this, of course, a little bit easy. You just find a match here and replace, the variable with the value which was below it. So here article with article 1. Where it is? These are our constants, so this must only occur there. Easy creator person. Person will be combined with person 1, and here's a variable name with Martin. And that's it. And we have here one, the first result, and in this case the only result of our SPARQL query. And that is just a simple way to visualize query processing with this graph representations. And maybe very easy to follow, I hope, very easy to follow. Right. Okay, here we have another more complicated example. Here we have a SPARQL query with 1, 2, 3, 4, 5, 6, 7 triple pattern. Here we have an RDF graph right here. And the task now is, of course, determine the query graph right here and draw all matchings into the RDF graph, and this is the result of the SPARQL query. Here we have the RDF graph, and that is just very easy. If we have here the query graph, or here's our query graph with the 7 triple patterns, 1, 2, 3, 4, 5, 6, 7, just right here. Then we must have some matchings in this graph. It's a query, what does it express? Here we have a citing article. We want to have the name of I start here. Here we have an article. No, this is cited, and this is the citing article. Okay, we start here. We have an article. It's of type bench article. We have some author inside, DC creator, cited author with some name. And this article is cited by another article, citing article that we ask for. It's also of type bench article, and we want now the name of the citing author. So we want all the combinations of authors who cited whom, right here. In our RDF graph, here it's the case we have 2 papers, they cite each other. Right here, sometimes this also occurs, but then of course they must already previously know that the other publication will occur right there. And the first article, A1, has 1 creator with name V, and the second has 2 authors. One is M and one is Q. No one thinks about James Bond, okay. Okay, we have here M and Q. There must be 0, 0, 7, no. It's V right there. Okay, and then we must find some matching. So, what is your guess? How many matchings will be here inside for this query? Is it 1? 2, 3, 4, 5, 6. How many do you think? How many? 2? One says 2. Other opinions?
12.
6. I hear 6. Does someone say 8? Or less?
Can you show the query again? Can you show the query again?
I can show the query again. Then I must switch to here.
12. 12. 12.
12.
Yes.
Answer is 12.
Answer is the question. So, you mean not the query, the question. Yeah. So we have 2 and 6. I just wanted to give you some time to just think about. So one matching can be right here with the green things. You can look at it. So A1 is here the, how it's called, this here the citing article, and A2 is the cited article, and the name of cited author is M, and B is the name of citing author. Do you agree? Good. Then we go on. Another matching is again the name of citing author is B, but the name of cited author is here also Q. Then we have already 2. But of course, this is in 2 directions. Of course, it can be also that easy cites, and this is the citing article and this is the cited article. This is the cited article, those name of cited author is B, and name of citing author in this case is M. And then we have another combination where name of cited author is Q. No, name of citing author is Q. I'm also confused about this, all these edges, and this is cited author. Yeah. Okay. I think that is it. So we have in the middle. We have 4 solutions. So we just have to take the average and we are right. Right here. If no one claims with the solution. If you see another thing and I make a mistake, of course, but I think that's all. Okay, that's it so far. These graphical visualizations are very fine for humans. You can maybe very somehow easily, of course, if it becomes so complicated, then you will be confused in which direction and so on are the matchings. It becomes much more difficult. That is, but maybe you can really easily visualize it. But when we come to relational algebra, then we must transform this query not to some query graph. We can also transform it into its operator graph, where the operators itself are operators of the relational algebra. Here we have a triple pattern, of course, in the standard relational algebra. There exists no operator for this triple pattern. We can come to this representation just by putting the triple patterns at the bottom, beside each other, then combine the triple patterns with the join operation. This is the symbol for join. And on top, on top, apply the projection operator to the variables which stand here after selecting. If he has a wildcard, then this project operator can be avoided, can be taken away. Okay. And the equivalent relational expression is right here. It's equivalent to this operator. And most times it's an operator tree, but sometimes you can optimize and can have some common expressions and so on, and then it will be a graph. That's why in general we also say it's an operator. So that's it right here. Then we must think about, okay, what is the semantics of each of these operations right here. And then, of course, we come to the relational algebra. It's very simple. And we must, of course, introduce the semantics of some further operators, like here the triple pattern operator. The triple pattern operator could be also seen as some form of index scan in relational algebra, plus some selection operator which filters out some results, plus some projection which binds the variables to the corresponding values, but you can also express it in some easy form where you say, okay, I have to go through all, or the result, not I have to go through all the input tuples, is not expressed in the right way, because of course we can do it better when we index the data. We have to check all tuples, or maybe have an index on it and access those more directly, such that all variables in the triple pattern are bound to the values in the input tuple that is expressed right here. I will go a little bit more fast on it, otherwise maybe we don't come to lunch. The pattern component is also a variable, or the constant of the pattern is the same as in the tuple that we must consider, and also if the same variable is bound 2 times in a pattern that we didn't check so far, like for example if p sides itself should not occur but we could express it, then we have to check if the values are the same right there. So we already, it's not a form of a join, but we should already then filter also those out where the if we have a variable that's a subject and object, for example, like here, p side p, then we have to filter out all those where the subject and object in the tuple is not the same. That we must also consider right here. So here is an example with tuples. So we have here A1 is of type bench article, I1 is of type bench journal, and A2 is of type article. And when we have here this tuple pattern, variable article, RDF type bench article, then of course the first and the third tuple matches, and we bind article to A1 and to A2, and this tuple here in the middle doesn't match because the object is different from that in the tuple pattern. That's pretty easy. Said that the input is a set of tuples. Up so far we have only sets, not something like multisets. Other relational algebra operators are projection, selection, cross product, union, difference, renaming some things that are already is a minimal set of operators, minimal in that way that the other operators until here can be expressed in terms of this minimal set of operators. There are also other minimal set of operators. Also, you should also know this. We have intersection operators, the division and quotient operator, which anyway we don't come to this. The join operator, and from here on we speak of the extended relational algebra, which extends the relational algebra with further features. You can say like this. Where we have the semi-join. I will explain them in more detail when we come to that point. Some outer joins, duplicate elimination, aggregation, grouping sorting, extended projection, and outer union. That is normally in the set of the extended relational algebra, and all these things cannot be expressed by the operators of the minimal set except min and max. Okay, when we come to this formal stuff, you must also know of what input type is it about. The traditional relational algebra was meant to operate on sets. So each element is only once contained, order of elements doesn't matter, and this set orientation or the sets are computed with in SPARQL and SQL, where you have somewhere or not somewhere behind the select keyword, the distinct keyword, such that duplicate elimination is processed, such that the result is a set. In reality, the query engines apply internally multisets or backs named. If there is a distinct there, then they sometimes also apply, or very often and most times also apply internally first multi-set operations, and at the end one time duplicate elimination. That is the most typical way how they proceed right there. In multisets, each element can occur multiple times. You can say, okay, that is like a list and not a set. But the difference to a list is that the order of elements doesn't matter. So it doesn't matter if this element is before the other, because of before the other. And in lists, it really doesn't, it matters. So if there's a list, then if the order is exchanged, it's not the same list, but if it is a multiset, it's the same multiset. That is just a small difference. Okay, operators of relational algebra. Traditionally, it's it has set semantics, but we often also look at the multi-set back semantics, as it is more close to the implementation in database management system. And as you already know from yesterday, at our institute, we developed such a query engine, and so I must also speak about these details. That is my profession. So here we have the projection. Projection normally has the sign peak, where you just here as attributes give the variables which should occur in the result of this projection, and the input is then some relation. We are now discussing, as I said, the relational algebra operators, and every time we are there, this stamp is there, just that you have an orientation. When we speak about SPARQL and when we speak about this relational algebra. Okay, here's an example. Here we have an order relation right here. And here we have a set semantics. The examples are also from relational databases sometimes, but the results of SPARQL expressions can be expressed in this way, except that we have their keys and except that we have there some foreign key relationships. That is normally not in the SPARQL expressions, but just the rest relations without keys and without foreign keys are typically white. Can be intermediate results of SPARQL expressions. Okay, and for this, in this example, we have here an order relation. Here we have the projection on the variables PID and CID on the relation order, and in set semantics, we see that PID and CID is 2 times the same right here, and in set semantics that is already eliminated, one occurrence of this, and the rest is just given only the attributes, or in SPARQL vocabulary often variables is called, is right, occurs right here, so this 10, 14 and 12, 15, and in multiset this 10, 14 combination occurs 2 times, quite easy. No? And there you already see 2 things, that of course the projection operator we must deal with in SPARQL expressions, and the second thing is that after the projection operator, we have a difference between multiset and set semantics. Before I said, okay, after the triple pattern, after we apply triple patterns, we anyway have set semantics, we have sets as results, but if we have other operators, then we come to the point where we must distinguish between multiset and back semantics and set semantics. Just say, if it is boring, just say, then I will go a little bit more quickly. So the natural join is the join which just combines input relations over the common variables. Here's just an example where we have 2 relations, one has the attributes A and B and one has the attributes B and C, so we have the common variables B, and the natural join just looks at common variables, and if they have the same values, they combine those tuples. So here it is expressed. We have here 2 times a 2 in this relation input relation R, and 2 times a 2 in input relation S. So we combine these two tuples, will give this result, 1, 2, 3, then 1, 2, 4, where it is? It's below. Okay, I will follow this notation. So we have 0, 2, I go here below, 0, 2, 3. It's just this. And we have 1, 2, 4, it's just here. And 0, 2, 4, it's just here. And then if we have only if we have in one relation something which doesn't have a join partner, it just thrown away. That is this tuple and this tuple, and here we have again matching results right here. And multiset is the same, except that duplicates, of course, can occur and every duplicated entry also will be combined. You know, so such that where we have it, here it is. Here we have 3 times the same, and all these 3 times we have results of it still right here, because they are all combined here in arms 3 and 4. So we have again 3 times 3, 4, 5. Again, just for the form. Okay, that's so far. Then we have different types of SPARQL queries. I think in this lecture we will only describe the select queries, which are the most important ones. But we have also construct queries, which return RDF data itself, which are, so the tuples of the return RDF data is determined by replacing variables in given tuple templates with the bound values of the query result right there. So we have an expression what can be the result there. Then we have ask queries, just come to that point, which just returns true or false based on a match of the query pattern or query result. Or it returns false if the query result is empty, and if it is unempty, then it returns true. Just like this. And we have also describe query which return RDF data which describes the determined query result. In some aspects, it's not completely specified what the result is in the specification. Just that you have an expression what can be also worked on right there, because of the time we only look at the select queries right here. And that we make much more extensive. Of course, there are also other operators like the union, and I can also have some formal stuff right here. What's the union? In set semantics, relatively clear. If a tuple occurs somewhere in one of the input relations, it occurs also in the result, but only once in the result. If it occurs 2 times, it occurs only once in the result. In multiset and back semantics, it's different. If the tuple, one tuple occurs n times in R and m times in S, then in the union of R and S, it occurs n plus m times. It's also relatively clear. So there's here the one example. So we have here 3 or 4 in R, and in S we have 2 times 3 and 4. So we have in the result 1, 2, 3 times the 3, 4 tuple. Now we must be very careful. Union in relational algebra requires that the schemes are the same of the input relations. And that is not the SPARQL union. The SPARQL union is the outer union. Just to have a short difference. It is like union, but it works with incompatible schemes. And the schema of the result is the union of the attribute sets of the input relations. And the missing values will be set to some null value. So here we have A and B as attributes in R, and A and C and S, and the result of the outer union is that the schema is an ABC, all the attributes right there, and then the duplicate, the tuples are just occurring there inside, and missing values are just complemented with null values. And the SPARQL union is exactly this outer union, and of course we can have set operations, multi-set operations also for this, and have a similar meaning on this. Okay. And I think now we have already all those things ready for the first tutorial. That's why I stopped here with explaining the features of SPARQL 1.0. And but we will have a next lecture where we have also features of SPARQL, explaining some features of SPARQL 1.1 and some of 1.0. So there you will have a nearly complete overview of the things going on there, I think. So what we will look at are also optional expressions which are important, filter, which are selection operators in the relational algebra, some built-in functions. We don't look at construct, ask, and describe queries. Or we must finish. The light is switched off. We don't look at naming quefs, which is similar to different databases right there in relational databases. So you can import many different ADF quefs, give them some identifier, and can also consider this different RDF quefs in one query. It's also not possible in traditional SQL. Some extensions, of course, but in traditional SQLs you also have only one input database and not different input databases. So they already see that SPARQL is very much designed for integration of data. Some limit offset order by constructs do what you think they do, so they limit the query results, only give 5 results back. After a given offset and with order by you can sort results. And in SPARQL 1.1 we also will come to this point here. We'll have the minus operation, we will have grouping, aggregation functions, we'll have parse expressions in the graph that are also quite comfortable to express queries with that. We will have subqueries, select expressions, explicit assignments. We will have, I think that I also will not tell you updates because of the time, and more powerful built-in functions, library, and that's it. So, I'm already over the time. You have to stop me at some point if I take too much of your times and you need some break. In summary, we have already now looked at the RDF as data format of the semantic web. Its basic construct is a tuple, and the RDF data is merely a set of tuples right there. The SPARQL query language is an RDF query language which is ideally designed as query language for the semantic web and RDF. So its basic component is, for example, also a triple pattern, which is, with which you can match the single triples right there. And according to the triples, additionally, triple patterns can have variables inside, placeholders as components. And maybe you get already the expression that especially SPARQL 1.1 will be very powerful and you can express many queries with it. Again, I will say, I just will give the outlook. In the afternoon we will do much more SPARQL, and afterwards we will do a tutorial. I heard already that we go for that below in the lab, not after the break. I will give lecture, as I said, but in the late afternoon, somewhere downwards is some lab with some computers, and we will directly work on the computers for that, and you can query your first RDF data. Okay. First, some questions. Are there any questions so far? If not, I think you are already hungry.